Okay, so 5.4 day 1. Simplifying. Complex. Do you need that? Rational expressions. So the good news is we're really just doing like one thing today, but these can be a little bit complex right there in the name. So a complex rational expression is essentially just a fraction with a fraction in it. So it is a rational expression that has another rational expression either in the numerator or denominator. So let's do one, like a numerical one first, and then we'll get some some variables in there. So if we want to simplify there it is. Trying to find my examples on your homework is probably not effective. There it is. Okay. So we'll do 1/4 minus 1/3 over 3/5 plus 4. So these are really cumbersome because, like, I mean, first of all, if you ever got this like as an answer and then you wanted to try to like use it in another problem, it would be a real pain, right? Like these are not super easy to work with as is. And also, they don't really give us an idea of like the size of this number, right? You can't just like look at that and like be like, oh yeah, that's a little more than 2, right? Like there's no sort of like intuitive way of telling like what the value of this is. And so in general, like we never want complex rational expressions as like a final answer because they're just not practical to use for anything. So you will always simplify them if you ever have one in a problem or have one as an answer. You're always going to simplify it so that you have a single numerator and a single denominator. And I kind of like to think of it as like 2 or like 3 little problems. So some of these problems that are a little bit more complex, it can be easier to handle if you think of it, if you break it down into like smaller problems that you know how to do and are a little bit less intimidating. So in reality, what's happening here is you're taking this whole thing and dividing it by this whole thing. So we can really think of this as like a division problem. Like you don't have to write this. I'm going to erase it in a second. As like 1/4 minus 1/3 divided by 3/5 plus 4. And that's one way that you can do it. You can rewrite it like that and go from there. However, I found that a lot of students forget the parentheses when they go from that step to that step, which changes the problem entirely, right? If I didn't have these parentheses, what would order of operations tell me to do first? Yeah, that division, right? And it doesn't really make much sense if you look at it this way to like divide those two things first, right? And so just to avoid that mistake, instead of writing it like this, we're just going to keep it all in one fraction. But we can still think of like the top and the bottom as sort of 2 separate things and do them kind of one at a time. So in the numerator, I'm just doing a subtraction problem. So I'm going to look at 1/4 and 1/3 and say my LCM is 12. So I need to multiply 1/4 by 3/3 minus 1/3, and I need to multiply that by 4/4. And then now we'll just look at the denominator. And remember that that 4 is just 4 over 1. And so my common denominator here is going to be 5. And so 3/5 I don't have to do anything with to get my common denominator because it already has a denominator of 5. Although, like, if you like to write 1 over 1, that's fine, you can. It's just not necessary.
Can you clear fractions?
Depends on what you mean.
Like times the numerator by 12?
And the denominator by 12? So you can't, so the only time you can clear fractions is in equations.
Okay.
It is true that if you did 12 over 12 here, that would clear the fractions on the top without changing the value of the overall thing. But then you'd have a factor of 12 down here to deal with. So in general, we clear fractions in equations because we have another side of the equation to balance out the change that we make when we multiply by like 12 or whatever we multiply by. So plus 4 over 1, and then I need to multiply by 5 over 5 to get common denominators. And so then back to the top, we have 3/12 minus 4/12. And then on the bottom, we have 3/5 plus 20/5. So if I do that subtraction, I get negative 1/12 and then 23/5. One thing you want to be really careful of with these things is that when you get to this point, this fraction bar is like nice and long, because otherwise you end up like with this kind of stack and it's hard to tell what goes where, especially if you end up with something like 2/3 divided by 6, right? Like if one of them's a fraction and one's not, it's kind of hard to tell if that's 2/3 divided by 6 or if it's 2 divided by 3/6, right? So you want to just make sure that like you're really clear about what like the big fraction is and where like the small fractions are. So then at this point, this is a division problem. So we've done an addition problem and a subtraction problem, and then now we're going to divide two fractions. So we have our numerator divided by our denominator. And to divide fractions, we multiply by the reciprocal of the divisor. So negative 1/12 stays the same. And then we multiply by the reciprocal of 23/5. And at this point, I would factor so that I could cancel. However, like 5 can't be factored, and 12 is just like 2s and 3s, right? And 23 is also prime. So like I can kind of see without actually doing anything that I'm not going to be able to cancel anything out. So I'm not even going to bother factoring that 12 just because it doesn't do anything for me. So we end up with negative 5 over, 276. Which isn't super pretty, but it's a lot prettier than what we started with, right? And we can get an idea of its size, right? 5 over 276 is a really, really tiny number, right? Pretty close to 0, in fact. And so, like, just looking at that fraction, you can kind of get an idea of how big its value is, which is always nice when you deal with numbers. What questions do you have? Does that process make sense, kind of in general? Okay, so let's get some variables involved. Okay, so again, we're just going to start by thinking about the addition in the numerator and the subtraction in the denominator. So That way we've broken it down into like two smaller problems, and then we'll worry about the big fraction bar. So in the numerator, notice that there's a addition in one of my denominators. So I'm going to put that in parentheses. What do you think our LCM should be? So it's tempting to say x plus 5, right? Because we like already have an x in the other one. But notice that there's nothing you can multiply x by to get x plus 5. And the only operation we're allowed to use here is multiplication. So since I can't multiply anything by x to get x plus 5, that means I have to have a separate factor of x and a separate factor of x plus 5. So I'm going to need them both in my LCM. So I have 1 over x, and I need to multiply that by x plus 5 over x plus 5. And then, well, this has to be longer. And then I've got 3 over x plus 5. And I need to do x over x. And you'll notice I started working like across the page. Like I normally don't condone that. Like usually we work down the page. But in this particular setting, it's sometimes nice just to do the entire top and then do the entire bottom. And if you work across this way, you can do that without losing like your fraction as a whole. Because like some people like to like take them apart and do them separately, but then sometimes it's hard to put them back together correctly. And so if it seems to make sense to you and it seems simpler, like you can do the entire top across the top and then the entire bottom across the bottom without losing like your numerator and denominator. So let's just do that. We'll just finish out the top, and then that way we can really think of it as like two separate problems instead of bouncing from one to the other. So we have 1 times x plus 5 plus 3 times x over x times x plus 5. And it can be tempting here, right, to cancel this x plus 5. But remember, we can't do that because of this addition right here. So the entire numerator isn't factored. So, and in addition, like distributing this 1 doesn't really do anything for us, right? Like 1 times x plus 5 is still x plus 5. So this is really just x plus 5 plus 3x. Does that make sense?
So can we combine the x and the 3x?
Uh-huh. So we have 4x plus 5 and then x times x plus 5. And I'm going to go ahead and put this in parentheses because it contains addition and subtraction. And so now I'll come all the way back over here and do exactly the same thing in the denominator. So I'm going to get common denominators and then subtract. So our LCM here is going to be x squared, which means I don't have to do anything with 2 over x squared. It already has my common denominator. And then 6 over x, we're going to multiply by x over x. So we end up with 2 minus 6x over x squared. And I'm going to put that in descending order just because I figure I'm probably going to factor it later. Over x squared. So now we have a single fraction in the numerator divided by a single fraction in the denominator. So we're ready to write it as a division problem. So 4x plus 5 over x times x plus 5 divided by negative 6x plus 2 over x squared. And so dividing fractions is the same as multiplying by the reciprocal of the divisor. So we're going to keep that first fraction the same. And then times the reciprocal of the second one. So now we want to factor everybody and simplify. So 4x plus 5 doesn't have any common factors, and it's linear, so there's no exponents, which means that can't be factored anymore. And then I have x squared, and if you want to write x squared, so you can write your monomial factors, like factored out, like prime factorization, or if like you can see this as two separate factors of x, you can leave it as x squared. So whichever one like makes the most sense to you. I'll go ahead and leave it like this. Just I think it's helpful as far as canceling. So then I have x times x plus 5. X plus 5 doesn't have any GCF, and it's linear, so that can't be factored anymore. And then here I'm going to factor out a negative 2. So remember that you need to put that negative 2 in parentheses, otherwise you make subtraction instead of multiplication. And so x, 3x minus 1. Can I simplify? Yeah, we can cancel one factor of x, which is kind of why I wrote that x squared is x times x, just so I could see that. If you can see that without breaking down the x squared, that's totally fine. You can leave it as x squared and then cancel it. You just don't want to forget to cancel. And so then our final answer, it's not super pretty, but it's x times 4x plus 5. And you can leave that x on the other side. It's just sort of convention to put monomial factors first. And then negative 2 times x plus 5 times 3x minus 1. And we're done. So like I said, these are a little bit long, but yes, go ahead.
If you were to write it without the monomial in front, would that be wrong?
Like if it was after?
Yeah.
No, it's not wrong. It's just a convention that we usually follow. But as long as you're not changing the operation, then it's totally fine. Any other questions? Okay. You guys want to try one? So go ahead and simplify. Let's try 3 over x plus 1 minus x over 3. No, I won't do that to you. I'll make it a 2. Oh, try that guy. Minus x plus 6. So to factor that, I'm going to start by factoring out a negative 1 to get that positive leading coefficient. And then my AC is negative 6 and my B is 1. So I'll use 3 and negative 2. So one big fraction I have negative 1 times x plus 3 times x minus 2. And then 6 times x minus 1. What about x squared minus x plus 12? Can that be factored? It can't, right? Because I have a positive AC, which means both my numbers have to have the same sign. It can be really tempting to try to use like 4 or negative 4 and 3 here, but negative 4 times 3 is negative 12, is not positive 12. So even though that'll add to negative 1, it's not going to multiply to my AC, to my 12. And so that's just done. And this is not very exciting or satisfying at all, because only one tiny little thing cancels. What is that?
The 2.
Yeah, the 6 and the 2, like, I can take a factor of 2 out of 6. That's not very satisfying. But nonetheless, it is the answer. So I'm going to do, with that negative 1 and 3, I'm going to call that a factor of negative 3, just because there's no reason for me to leave them separate. So we have negative 3 times x plus 3 times x minus 2 times x minus 1 and then x plus 1 times x squared minus x plus 12. And we are done. I mean, we're not done. We're done with that problem. We still have more to do. Okay, let's do one that looks like a difference quotient. So we'll do one over x plus h minus 1 over x all over h. So we haven't really talked about y yet, but this is an example of a type of rational expression called a difference quotient, which is kind of the basis for calculus. And we're going to work with difference quotients all day on Monday, but it's kind of the place in the immediate future where you're going to see these rational expressions most often. And so I'm just trying to like give you a chance to do a billion of them before you get to calculus, because then the simplifying of them won't be challenging because you'll already have it. So lots of x's, h in the bottom is pretty much how they all look. So we're going to simplify it the same way we did before. It looks like there's no numbers in this, right? So that can make it look a little bit weird, but we want to treat it the same way we've been doing the rest. So we're going to just simplify that numerator, and really, like, there's nothing to do in the denominator here, so you just want to bring that denominator with you in every step. Be sure not to lose it, because if you drop it in the beginning, it's pretty hard to remember to put it back in at the end. So we're just going to carry it with us. So we have to put parentheses around our x plus h, right? That's a separate factor because there's nothing I can multiply x by to get x plus h. So I can't combine those in any way. I just have to have a single factor of x and a single factor of x plus h in my LCD. So we have 1 over x plus h and I'm going to need a factor of x minus 1 over x times x plus h over x plus h. And then again, like that h is just coming along for the ride. So then in the numerator, we have 1 times x, which is x, minus 1 times x plus h over x times x plus h, and then all of that is over h. So if you didn't want to write like this 1, like you certainly don't have to write that factor of 1, but you do need those parentheses. So if we lose these parentheses, then we don't end up distributing that negative, right? So that's one of the reasons I kind of just copy in that step, is so that I don't make sign errors because of how I've translated from one step to another. So I just kind of rewrite it and then figure out what I need to do from there. So I'm going to distribute that -1. I hate it when my equal signs aren't centered. All over h. And then notice that x minus x is just 0, and so when I combine like terms, those two terms just go away. So I have -h over x plus h divided by h. So we'll write that as a division problem. So what's the reciprocal of h?
H over 1. I mean 1 over h.
Right, so h is h over 1, good, and then the reciprocal is 1 over h. So we have -h over x times x plus h times 1 over h. And it turns out that we can cancel those h's because -h is really just a factor of -1 times a factor of h. So we can kind of separate that negative from the h, which allows us to cancel the h. It's one of the nice things about difference quotients, which we'll see on Monday, is that like the h always cancels. So it's super satisfying, like when you get to the end, because like you know you did something right because your h cancels and you're like, yay, everything's good. This is the kind of thing that excites some of us. Okay, so then we end up with -1 over x times x plus h, and that's our final answer. Isn't this fun? Mm-hmm. Here, you guys try this one. Let's do 1 over x plus 2 plus 4 over x minus 3 and 2 over x minus 3 minus 7 over x plus 2. Okay, give that one a shot. Not excited. So from here to here, I clearly like skip some stuff. But notice that the denominators are exactly the same in the numerator and denominator in that step. And if you look at your work and you wrote it all out, notice that you ended up just canceling that x plus 2 times x minus 3, because when the denominators are the same and you take the reciprocal of one of them, it just one of the numerators and one of the denominators are the same. So when you're dividing two fractions and they have the same denominator, you can actually just like cancel them right off the bat. So if the denominator of the top and the denominator of the bottom are exactly the same, they will always cancel. And so that's how I got like from there to there without like writing all that division and multiplication out. If you're not comfortable taking that shortcut, then by all means, like write it all out. But, and then in the numerators, I just combine like terms. Okay, we have 1 minute. I can give you back some stuff so that you can do corrections. If it's not yours, just pass it back.